Okay, last up in chapter 3 is concentration. So this semester we kind of focused down on one concentration unit called molarity. Molarity is given the symbol big M. Whenever you see a big M, it translates into a fraction. And now we can see why this is in chapter 3 because fractions are conversion factors. They're a way for us to take one bit of information and turn it into another. Big M translates into moles of solute per liter of solution. We all have a general idea what concentration is. Think about like any kind of drink that's a mixture, iced tea, something like that, where if it's darker, it's more concentrated, there's more tea in there, okay? That's what we're talking about here. We're just quantifying it instead of grams, instead of taste. We're actually looking at a volume sample of a mixture and we're figuring out the moles of the things that we dissolve in there, right? So just a couple bits of verbiage to get used to. We're going to focus in on aqueous solutions this semester, okay? Let's go down here first. Solutions are the mixture. We kind of know that from earlier in this chapter, okay? You'll see me abbreviate solution SOL. This is a superscript small n with an underline. We just get so like lazy. Instead of writing solution, we always write SOL, superscript n with an underline, okay? So you'll even see that up here. Like when I was just writing solution, I just naturally do it. And you're allowed to do it too. I mean, it's just a nice little simple way to write solution. This semester we focus in on aqueous solutions, which means that water is the solvent. We're going to talk specifically about salts that dissolve in water, okay? Salt is another word for an ionic compound, okay? So this semester we focus in on how ionic compounds, which we call salts, dissolve in water, okay? Solvent, all right, the solvent of a solution does the dissolving. So it's the thing that you're putting, all right, the object you're trying to dissolve into. In the case of this semester, our solvent is going to be H2O. The solute is the thing that you're dissolving. This semester, that's going to be ionic compounds or salts, right? The solution is the solvent and solute together. It's the mixture that you make, all right? So the solute has a certain concentration. And the more solute you have in there, the more moles that you have in that set volume of solution, all right? The more particles you have, all right, the higher concentration that you have. The dissolution process in water is sort of shown down here pictorially, okay? So I just want to explain this because developing this picture, this sort of model in our head of how the dissolution process works is essential for understanding not only this section of chapter 3, but in chapter 4 we talk a lot about salt solutions, okay? So this we should be familiar with. This kind of looks like an ionic compound. We view ionic compounds as pluses and minuses, where an electron exchange had occurred, and now the positive ion, the cation, and the anion are stuck together. Whenever you see an arrow in H2O, what that says is, all right, we're putting that salt in water. Well, what happens when we put that salt in water? The plus and the minus, they actually stop holding each other, okay? There's complicated chemistry that occurs, but essentially what you want to know just from a fundamental standpoint is water gets in the way. Water can pick these guys apart, and then water surrounds each ion. When we talk about an aqueous state, this is what we mean. We mean that it's no longer a plus and minus stuck together. It's changed its behavior. It's changed its sort of physical setting. And now it's not a plus and minus stuck together like its solid state before the dissolution process, but now water is separately taking away the plus and the minus and surrounding the cation and the anion. Okay? So whenever we talk about molarity, right, we're going to be saying, hey, we're going to put these solids in water. The water is going to act like a solvent. These solids are the solute. We're going to make a solution, right? And inside that solution, we realize that the pluses and minuses are all floating away from each other. Okay. All pluses and minuses break apart and float away from each other. Polyatomic ions stay together. Remember, we kind of drew polyatomic ions as big circles, but pluses and minuses, they all go away from each other. Everything breaks down and is floating far away from the structure that it used to be. Okay, so now with that physical picture established, and some wording in play. Essentially, the math associated with looking at these types of systems is all about using this fraction as a conversion factor. When we talk about using molarity, all right, if you notice here, all right, we have another avenue to get moles. Moles have been playing a critical role in how we convert information from one species to the next. Moles can give us mass information, right? Moles are hidden inside big M. Moles are hidden in molarity, right? So you hear me say this a lot. Molarity times volume of solution gives you moles of solute. And that's just a fundamental thing that you'll use in like pretty much almost every chemistry course from here on in. Molarity times volume gives you moles. All right, molarity times volume gives you moles. So let's do a couple examples with this in mind. Let's go through, like I said, not only looking at dissolution, but then applying some numbers to the process and calculating molarities and figuring out masses needed for salts to go in solution, etc. Let's look at a couple different practical examples involving this value as a conversion factor. So example number 1, all right? We have 5.00 grams of K2O, and we're dissolving it in enough water to make 500 milliliters of solution. And what we're going to be asked for is what is the molarity of K2O after we do the dissolving, and then what's the molarity of K plus? Because we realize that once the dissolving occurs, it's not just full K2Os that are floating around, there's also free floating K plus in that solution, all right? I like to start these problems by staying organized through the writing of a dissolution. Now this looks like our model that we drew before, where we just had a plus and a minus, but now we're showing symbolically what the chemical is doing. So what happens when this guy breaks down? Remember I said all the ions here break apart and fly away from each other, okay? So the oxygen, I'm going to write that first, picks up its -2 charge, right? And it's surrounded by water molecules, and so we say that it's aqueous, all right? Now, some students have an instinct to try to keep these K's together, right? And I'm going to write a mistake over here. K2 plus 2 aqueous, all right? And hopefully you can look at this, all right? And you can write down in your notes and you can see that this is a big error. This is not correct. And hopefully you'll know to never ever do this. What does this imply, this 2 down here? This implies that the K's are stuck together. But what really happens from a symbolic standpoint, we have a -2 oxide anion, and we have 2 K pluses. And those pluses, they don't like to be near each other. And so when this breaks down, right, the plus floats away by itself, the -2 floats away by itself, the oxide anion, and then the other plus is not attached to the other plus. There's water surrounding everything. All the ions break apart completely, okay? So what we'll have here in reality, and the correct way to complete this problem, is essentially what happens is you get 2 separate K's floating away from each other. You get 2 K plus. Now they are surrounded by water, so we're going to give them the state aqueous. But now you can see how that symbolism leads us to write these dissolution problems in a way that makes sense. This breaks down into 2 K surrounded by water and 1 O surrounded by water. Notice I include the correct charge. And also notice that there's no charge over here and there's no net charge over here. 2 pluses cancel out the -2. So then let's think about the information that we're given, all right? We want to know, all right, based off of 5 grams of K2O and 500 milliliters of solution, what the molarity of K2O is. Well, let's write down our goal. Molarity is going to be moles of solute. So what's the solute here? Okay, K2O is being dissolved, all right? The denominator is always liters of solution, So essentially I have another problem where if I want to create this conversion factor, right, the goal is to create molarity. Then what I need is two separate bits of information put together in a fraction that I can then divide and answer from there, right? So let's do this step by step, right? Oh, moles of K2O? What information am I given at the top here that gets me moles of K2O? I know I have 5 grams of K2O, and I know that based off of information on the periodic table, I could determine that there's 94.20 grams of K2O in every 1 mole of K2O. I can do a mass to mole conversion. And what I get when I do that is I get 0.0530786 moles of K2O. In terms of my final result, the thing I'm trying to calculate, okay, this is going to be the numerator. Now I did math, so what am I going to keep track of? Significant figures. 0.0530786 moles of K2O. Right. Now that's not the molarity because molarity is moles of solute per liter of solution. So I still need this denominator. But am I given solution information? And the answer is yes. So in this case, right, I'm given 500 milliliters of solution. Okay. Do I know how to get liters of solution from milliliters of solution? Well, sure. 1,000 milliliters of solution is 1 liter of solution. Right? 1,000, not 100. Okay. This number then, I'm just going to stick right here. Okay. So when I do this, I get 0.500 liters of solution. Now, why did I not write that as 0.5? There's 3 significant figures here. This is exact, so there would be 3 significant figures here. So I plug this into my calculator. I take the moles that I calculate. I take the liters that I calculate, and putting them together in this fraction gives me a molarity, rounded to 3 significant digits, of 0.106 molar K2O. Okay. Now, from here, we can finish the rest of the problem. And what the problem says now is, well, what about K plus, right? K plus is going to be floating around in here. We figured out how many moles of K2O we dissolved, but what happened when everything broke down? Can we focus in on just one individual ion and look at it as a separate entity? And the answer is yes. Well, what would the molarity of K2O look? Oh, sorry, the molarity of K plus look like? Well, I would need moles of K plus and liters of solution. Okay. So what changes about the analysis, or what information do we already have? Do we already know liters of solution? Well, sure, it's there. What other information do we have? We have moles of K2O. So I have moles of K2O, and to complete the second part of the problem, I need moles of K plus. These differ by an identity, and they're both moles. So what can I use to figure out how to go from this calculation to this? I would need a mole-to-mole bridge, right? And if I look here, hopefully you can see, for every 1 mole of K2O, there are 2 K pluses that get produced. So right here, I don't have room, but what you could write down to finish this problem is you could say, okay, moles of K2O, for every 1 mole of K2O, there's 2 moles of K plus. So essentially it looks like the exact same setup, except now we also have an extra multiplicative factor of 2. And that makes sense because for every 1 of these that dissolve, you get 2 of these, okay? So the final answer for the molarity of K plus, okay, and make sure you confirm this, is 0.212 molarity K plus, all right? What do you think the molarity of oxygen will be? Well, the molarity of oxide, all right, I should say oxide, not oxygen, the molarity of the oxygen anion, right, would be the same as the molarity of K2O. How do I know that? Because when I think about doing the mole-to-mole bridge, there's a 1-to-1 ratio here. So actually the molarity of O minus 2, which we didn't ask for here, but it's good to know and it kind of helps with your understanding. The molarity of O minus 2 would be 0.106 molar O minus 2. Okay. Let's do another example. What mass of KCl is needed to produce 25.00 milliliters of solution with a concentration of KCl that's equal to 4.0 molar. All right. So this kind of fits a form of a problem we're familiar with. It looks like we're asked to analyze something. It looks like we're trying to convert it to a different bit of information, and we're also given information to use in the problem. This feels like a conversion problem, and I mentioned at the very beginning of this video, molarity can be used as a conversion factor. So what do we do for our general problem solving skills here? We take what we're trying to analyze, 25.00 milliliters of solution, we write on the left hand side. We're trying to get mass of KCl, so let's get grams of KCl on this side. Now normally our next step is to analyze and say, hold on a second, all right? These are different identities, so we need a mole to mole bridge in the middle, but for these solutions, right, that have a molarity, there's a different thing that links solution to solute, and it's molarity, right? And what I like to do at the beginning of these problems is write down the molarity information that I'm given as a conversion factor. So I don't leave this big M as a big M. I write it as 4.0 moles of KCl per liter of solution. And that reminds me that this is the thing that links in these types of problems, all right, solution information to moles of solute, right? So then I have everything I need to go ahead and do this problem. Because if I can get moles of KCl, can I get grams of KCl? Well, sure. And if I can get liters of solution from milliliters of solution, okay, yeah, I know how to do that. Well, then I can link everything together and get grams of KCl as needed, all right? So let me write down all the intermediate steps here. We would first go to 1,000 milliliters of solution is 1 liter of solution. And now that we have liters of solution, what we can do is we can write down for every 1 liter of solution, there's 4.0 moles of KCl. And you keep going in your work towards the right. I have to go down just from based off a space issue, okay? So now, if I know I have 1 mole of KCl, I can look on the periodic table and I can determine that there's 74.55 grams of KCl for every 1 mole of KCl. And then I hit my final unit that I need. And I see that everything cancels, and what I get is at the end, right, 7.5 grams of KCl, right, 7.5 grams of KCl. Now, why did I round the 2 significant digits, right? This is a measurement with 4 significant figures. This is exact. Molarities are measured, all right? We would need to determine them experimentally. There's 2 significant figures here, there's 4 here, so my answer just has 2 significant figures. So that shows you molarity acting like a conversion factor, right? I want to do one more conversion type problem. This kind of harkens back to the beginning of the chapter, just as a little review, all right? You have 300 liters of an Li3P solution that has a concentration that's equal to 5.00 molar Li3P, right? How many Li plus ions are in solution, right? how many Li plus ions are in solution. So it looks like we're told to analyze something. We're asked to analyze 3 liters of solution. That goes on my left-hand side. We're given a concentration of 5 molar. Remember, I like to write big M as 5.00 moles of Li3P per liter of solution. I like to break it down to see the conversion factor at the beginning. And what are we trying to get to? We're trying to get to number of ions. We're trying to count, right, the number of lithium plus ions, right, that result. Now, Li3P, when we put it in water, what does it break into? It breaks into 3 Li pluses plus a P minus 3. And both of those would be aqueous. And that's implied by saying that there is a solution. So lithium phosphide breaks into 3 Li pluses and a P minus 3. Okay, so different identity, have to get to moles somehow. Ooh, I do have this, that helps. Next step will be, for every 1 liter of solution, there's 5.00 moles of Li3P. If I know moles, I can count using Avogadro's number. But Li3P is not Li plus. Oh, wait a second. I realize that with the dissolution process, I know that for every 1 mole of Li3P, we get how many Li pluses? 3 moles of Li plus. And then I can use Avogadro's number. For every 1 mole of Li plus, how many Li plus ions are there? 6.022 times 10 to the 23rd Li plus, all right? I use Avogadro's number, and my final answer to the correct number of significant figures is 2.71 times 10 to the 25 Li plus ions. So that's how we can count, right, using Avogadro's number, even for these problems, okay? So the reason I bring this up is a point I made in an earlier video. You don't view this as one type of problem. It's another tool that you fit into your basket of tools, into your tool belt, right? It's another tool that you have to see as a conversion factor. So you try to learn the general conversion factor techniques to enact the use of that tool, okay? One last topic in this chapter, and that is dilution. So going back to like something I mentioned earlier, iced tea. All right, so if I put more water into the iced tea, I create a bigger solution, a more voluminous solution. And the iced tea becomes less concentrated. We call that process a dilution. All right, a dilution. Now, the way that you're going to identify a dilution is it looks like there's no reaction going on, and it's that like iced tea example. It looks like you're putting more volume into an already established solution. All right? So what happens is, and what you have to realize is that the moles before are equal to the moles after. So if I have something in a beaker, right, and it's floating around and it has a certain concentration, right, and let's just draw cations as orange and anions as red, and we know they're surrounded by water, okay? And I dump in more water, creating a bigger volume of solution. Have I changed the amount of stuff that's in there? Well, no. It's the same orange and red swimming around. It's just it's swimming around in a bigger volume. The volume of solution's in the denominator. So the solution becomes less concentrated, all right? Because there's the same amount of moles in a bigger volume, all right? And so whenever we look at a problem and we read it and it looks like this scenario is going on, I'm analyzing a solution and there's no reaction happening, but it looks like I'm changing the volume, then what we have is a dilution, and every dilution problem is solved the same way. M1V1 equals M2V2, all right? The concentration is changing here. M1 is viewed as the concentration before you dump more stuff in there. The concentration before is in a certain volume. M2 is the new concentration in the new volume. So pictorially, what we would have here, right, is a V1, right, represented by that initial amount of volume. And then inside that volume, there would be a certain M1, right? But has the concentration changed when we increase the volume to this V2? Well, sure. And we expect M2 to be less, right? M2 to be less than M1. We expect the concentration to go down when we do something like that. Oh, moles before is moles after? What did I tell you in the previous little discussion that we had? Molarity times volume gives you moles. So my molarity before and my volume before is equal to my molarity after and my volume after multiplying each other. Moles equals moles. Okay. So it's a pretty simple process. What students run into in terms of an issue is trying to use it when they shouldn't. So just always do that check. Does it sound like I'm just kind of changing volume? Okay. Does it look like I'm removing or adding volume and there's no reactions happening? Then you always start with M1V1 equals M2V2. All right. Quick little example to finish this out. Okay. A 0.20 molar solution, right, is to be used to construct, all right, a 0.15 molar solution with a volume of 500 milliliters. How much or how many milliliters of the 0.20 molar solution are needed? Right. So this fits our dilution identification step. This fits what we said, and it kind of fits the picture that we had before. Because essentially what we're asked about is a volume of a concentrated solution. So we have a certain solution, all right, and it has a certain volume. And we have to turn it into a solution with a different concentration, right, and a final volume. There's an interplay between an M and a V and another M and a V, all right? There's no reaction mentioned. They're not even telling you what the solution is. They're just saying, hey, there's a certain concentration. We want to know how much of it we need to create this solution that has a very specific concentration and a very specific volume. This is M1V1 equals M2V2. When I analyze this, I like to make sure I don't sort of mess up which M goes with which V. So if I'm going to call this M1, I'm going to remind myself that the solution that's being referenced here in terms of the many milliliters or how many milliliters we have at the end would be my V1. These two guys are linked. And by the wording of the problem, that means that this is linked to this. Okay? So M1, V1 is going to go on one side of my equation, and this particular M and this particular V are going to go on the other side of the equation. Right? So we have this written down. Now let's enact the mathematics. All right. Remind you, M1 V1 equals M2 V2. Remember, we're trying to solve for V1, so let's just do that algebraically. M2 V2 over V1. If I look at my labels that I had before and my understanding of the problem, all right, M2 was 0.15, oh, sorry, V1. To solve this algebraically, I'm going to divide both sides by M1. Sorry about that, right? M2 was labeled as 0.15 molar. V2 was 500 milliliters, okay? My M1 was 0.20 molar. So that gives me a way to solve for V1. And when I do this, I get 380 milliliters, right? It's 380 milliliters. Now, why does my answer only have two significant figures, right? I go back and think mathematically what's occurring here. 2 sig figs, 2 sig figs, 3 sig figs. My answer should have two significant figures. So even though your calculator shows you 375 milliliters, I'm going to write it as 380 milliliters, indicating that that zero is not a significant digit, right? That's really it for dilution, okay? It's just about recognizing when to use it and making sure you identify the correct M and V and M and V combination. But all it is from there is a simple algebraic problem where you have an equation with four unknowns. You look for three of them, you make sure they're on the correct side, and you solve, all right, for the information that you're trying to get, okay? So that's it for chapter 3 then.